performance for particle applications on early exascale machines. And these are examples from the libraries in our partner apps from the Co-design Center for Particle Applications. Each of our speakers will give a short talk, and then if you have a question or two, we can answer it then or wait till later when they're all done. So let's get started. First, Stan Moore, take it away.
Thank you, Sue. So I'm Stan Moore from Sandia National Laboratories. I'm part of CoPA, and I'll be speaking on LAMP's performance on Crusher. Okay, so just a little bit of intro to LAMPs as well as Exalt. So CoPA is trying to help the Exalt KPP performance. LAMPs is a parallel classical molecular dynamics code. So we are modeling the interaction of atoms, but neglecting electrons, so in a classical manner, using Newton's equations of motion. Exalt, the ECP Exalt project is trying to extend the accuracy, length, and time scales of molecular dynamics with emphasis on material science simulations. And instead of the typical exascale problem of running, as large a problem as possible, say billions of atoms, Exalt is trying to run millions of small replicas, so say 1,000 to 1,000,000 atoms, and stitch them together in a large trajectory to enable long time scales. And the primary KPP of Exalt uses the SNAP machine learning potential, and SNAP is very computationally expensive, and so there's other parts to Exalt, but SNAP is really the bottleneck, and so our KPP basically depends on SNAP performance on a single node, because again, we're running replicas instead of one large weak-scaled simulation. Okay, so the team for improving the Exalt KPP on GPUs is large. It's I'm not going to name everybody, but it's a large collaboration between vendors, including NVIDIA and AMD, as well as multiple labs. So there's a lot of work that went into this with a lot of really awesome people. And here is our progress to date. We've seen an incredible 25x speed up for the Exalt KPP on V100 in approximately ECP timeframe. And so this is performance versus time. And so basically this is our baseline and all the way up to our latest performance. And I'm not going to list all of the improvements that went into this 25x speed up, but I just wanted to point out that it's a combination of both algorithmic and implementation improvements, and a lot of work by a lot of people. Okay, so the previous plot I showed just the V100 performance, but we have all of these intermediate SNAP versions, and I took these and I ported them to run with the recent LAMPs, recent CoCos on different hardware. So we were optimizing for Summit V100, but then we can take all the versions and run them on other hardware that weren't available at the time that we made the improvements. And one thing really stands out is that the V100 is an excellent proxy for MI250X. So incredibly, all of the improvements for V100 also helped MI250X performance. And if we compare the first plot with the latest plot, you can see that we get about 25x performance improvement for both V100 and MI250X. This is because if you look at the inset, you can see that the green curve MI250X is a little bit, the baseline performance, or in January 2018 was a little bit less than V100. And if I run, so this is a little bit out of date. If I take the latest CoCos, Rockham, and LAMPs, and rerun the last data point, we get about 4% additional improvement on MI250X. So this is just saying, optimizing for V100 was an excellent proxy for Frontier. But one thing stands out. Why is MI250X performance for one die only about 0.7x V100? So if we look at the achievable flop rate or achievable flops, it should be, closer to 2.5x, and we're less than 1 for snap. And so we're going to look more into that in the next few slides. So I profiled snap on V100 and MI250X using NVProf and RockProf. And there are 3 main kernels in snap. The first is compute YI, which is about 2/3 of the runtime on both GPUs. And then the next is fuse DIDRJ, which is not quite 1/3 of the runtime. And then a smaller last kernel, compute UI, which is about 3% or 5% of the runtime. So by far, compute YI is the largest kernel. We know from previous work that compute YI is L1 cache bandwidth bound on V100. Fuse DIDRJ is compute bound on V100, and compute UI atomic add bound. And then in this work, we profiled compute YI on MI250X, and we see that it's currently VALU INT32 bound. So I'm going to talk more about that. But I do want to point out that I did use fast hardware atomics on MI250X, which gave a significant speed up. Like I said before, one of the kernels is atomic add bound, so it does help quite a bit. Okay, so Nick Curtis from AMD profiled compute YI on MI250X, which is, like we said before, the largest kernel in snap. And he found that it's 90% VALU, or vector ALU, INT32 bound. So we're only waiting on memory for about 10% of the time. So it's definitely not L1 cache bandwidth bound like on V100. And so where is all this INT32 overhead coming from? Well, Snap actually uses up to 40 arrays in deeply nested loops. And so there's a large INT32 overhead to compute the offsets and index into these 40 Cocos views. And so one thing that Nick is doing is he's working to get the AMD compiler to generate integer fuse to multiply add operations, or IMADs. And he actually has a hack where he was able to get a 5% end-to-end speed up in Snap for if he hacked in some IMADs. Another thing that Nick noticed is that there seems to be some overhead of the MD range policy in the Cocos HIP backend. So he has the Cocos kernel versus a raw HIP kernel that he wrote by hand, and he can see that there's some overhead in the Cocos HIP backend. He did the same for CUDA, and there's not as much overhead for a raw CUDA kernel using MD range policy versus the Cocos CUDA MD range policy. So we think that there could be some improvement here. Another thing that could help this INT32 issue is using Cocos subviews. So similar to pre-computing pointer offset at the beginning of a loop, we can use a subview which reduces the dimension that we have to index into the Cocos view, but this also increases register pressure. So we're not sure if this will be a win or not, but it's something that we're going to try in the future. So why isn't this a problem on V100, this INT32 bottleneck? Well, for one thing, the NVIDIA compiler can successfully generate the IMAD operations, these fused multiply add, which are used in indexing into the Cocos views. And that's one thing that we hope we can get the AMD compiler to do as well. In addition, V100 has independent integer and floating point data paths, so you can overlap integer and floating point computations. And so this basically makes integer math free on V100. And so if adding subviews is beneficial for AMD GPUs, it will most likely hurt performance on NVIDIA GPUs due to the increased register pressure. And so if we do end up adding subviews, then we'll probably have to use an abstraction to use the subviews for AMD and the full views for NVIDIA. Okay, so here is a comparison of the hardware on Frontier versus Summit. So the MI250X GPU for one die has 24 teraflops of FP64 compute, theoretical. If we run a compute-bound benchmark called CoCo's bytes and flops, we can get about 18.3 teraflops. And then Nick Curtis also has a raw hit version of the same benchmark, and you can get almost 20 teraflops. On NVIDIA, it's 7.8 teraflops. But one thing that really stands out is this L1 cache size on MI250X versus V100. You can see that the L1 cache size per SM on V100 is 6x larger than on MI250X. And this corresponds, if we look at the L1 cache hit rate for our largest kernel in Snap, it's only about 60% on MI250X versus about 90% on V100. So unfortunately, even if we fix this int32 bottleneck, which hopefully we can, Snap performance will probably still be limited by this smaller L1 cache on MI250X. And we can do a numerical experiment to show that this is indeed a large issue. So on V100, there's a unified cache. You can actually change the size of the L1 cache because it's shared between L1 and the shared memory. So by default, the L1 cache size is 96 kilobytes per SM. We can reduce that by a factor of 3, so there's only 32 kilobytes, and measure the L1 cache hit rate, and it drops down to about 60%, which is similar to what we saw on MI250X with lamps. And the performance similarly drops by a significant amount. And this significantly closes the gap between NVIDIA and MI100. And so this bottom line is this L1 cache size has a huge effect on Snap performance. And because it's 6x smaller on MI250X, this is going to be a limiter for, ultimate limiter for Snap on Frontier. Okay, so previous results were all single GCD, single die. The power is shared on a node, and so using a single GCD may not be realistic because this single GCD can get more of its fair share of power, but that doesn't seem to be the case for Snap. So I ran a single replica on all the GCDs, 8 on a single node, and we only get about 5% difference. And so, basically Snap isn't power limited, and the single GCD benchmarks are valid. This may not be true for a different benchmark in LAMP that's more compute bound. Okay, so we talked about a lot about Snap in LAMPs, the machine learning potential. There's another model in LAMPs that is also important, the reactive force field, or ReaxFF. It's a Coral 2 benchmark, meaning it's used for acceptance testing on Frontier. And it was featured in AMD's MI200 public release. And AMD, so Nick Curtis, Leopold Grinberg, and Gina Sitarman contributed several improvements to ReaxFF, for which we are very grateful. They did a lot of great work on ReaxFF. And their work and their good ideas spurred additional improvement from NVIDIA, Evan Weinberg, as well as myself. And so since February, we've seen 1.5x cumulative speed up on MI250X, and almost 1.7x speed up on V100 for a ReaxFF benchmark. And all of these improvements have been released in public lamps. So this is great work. We're very grateful for the vendor support that we've had for REX as well as Snap. Okay, and here is a slide on different benchmarks in lamps. So going from the least expensive Leonard Jones, which is memory bandwidth bound, to very expensive benchmarks such as REX and Snap. The performance is in time steps per second, so you can't really compare benchmark to benchmark because they use different system sizes, but you can compare V100 to MI250X. You can see that our best benchmark as far as comparing MI250X to V100 is REX, so we get just a little bit over 1x speed up, and so this is 1 die versus V100. And our worst benchmark is EAM. So EAM uses a spline lookup table. It's a 3D CoCo's view. It's not as heavy as Snap, so there's not as much compute. And so it may suffer from the same int32 indexing bottleneck that we saw with Snap. We need a profile to know for sure. And just a caveat, we believe that there is some room for improvement in the AMD runtime, CoCo's hit backend, and maybe even in lamps, such as reducing synchronization and memcopy latencies. And so take this performance as preliminary, not as final. There could be room for improvement. So in conclusion, the Exalt project is on track to meet and probably greatly exceed this 50x target for comparing full Frontier versus full Mira due to the 25x Snap improvements over the last several years. If we look at the most expensive Snap kernel, Compute YI, currently it's ALU int32 bound on the AMD GPUs. But we're hoping that we can fix that. But even if we do, it's ultimately limited by the smaller L1 cache as well. REXFF does best on MI250X relative to V100, so it's actually a little bit faster on MI250X, 1 die versus V100, but it's still roughly only, about 1-to-1 performance. And if we just look at the flops, it should be more like 2.5x. But unfortunately, LAMP's GPU performance, as we've seen in Snap, depends on more than just the peak flops. The L1 cache and int32 throughput really matter for LAMPs. But there is some hope. We hope that the AMD compiler can be improved. So we talked about the IMAD ops that can be generated. There's also a CoCo's pull request that adds restrict the driver type to help the compiler and gives a speed up. We talked about the MD range policy. Hopefully that can be improved in the CoCo's hip backend. There seems to be some overhead versus raw hip. And then perhaps using subviews can reduce the int32 indexing cost. But we're not sure because it also adds register pressure. So we're not sure if that'll be a win or not, but that's something that we're definitely going to look into. And then again, this is all a work in progress. There may be other improvements that we don't know about, other changes that we can make that can improve performance. So, I've tried to show the current reality, but also hope for the future for other improvements. And with that, I'll take any questions. Thank you.
I have one question. So what profiling tools did you use to do the to figure out what the L1 cache performance was on AMD?
So that was work done by my collaborator Evan Weinberg, and I believe he's using the Insight tools, systems and compute.
Oh, I see. And when you did your experiments to reduce the L1 cache size that's configurable on the V100, you did that. How exactly do you go about doing that when you're running a CoCo's application?
So there's this cache config variable that you can set. So you set it either to prefer L1 or prefer shared, and that's just kind of a preset. It'll give you these values of L1 versus shared memory. I think there's a way to do that on Cocos. If not, it's definitely an NVIDIA argument that you can pass in.
Oh, okay.
Yeah. Yeah, and Cocos has some heuristics to set this automatically. Any other questions?
Thanks, Dan.
Yes, thank you.
And let's move on. Our next speaker is Steve Rangel, who will talk about Hack Cabana.
Thanks. Okay, can everybody see my screen?
Yes.
Great. Yeah, so my name is Steve Rangel, and Adrian Pope is also on the online right now. And we're talking about Hack Cabana, which is a proxy app for cosmological embodied code called Hack. So this proxy app is basically trying to model the short range solver that's used inside Hack using the Cabana library. So Hack is solving Hack is solving the Vlasov-Poisson equations in order to compute an embodied cosmological simulation. So this is computing the forces of gravity in an expanding universe, and we're using particles as tracers in this 6D phase space to this problem. And the way Hack goes about sort of achieving this is using a force fitting technique, where the long range force of gravity is computed using a spectral method, and the short range force of gravity is added to overcome the shortcomings of using a particle mesh method. And together the forces are added together using a polynomial. So the way this looks sort of as far as how the algorithm works, for what we call a high res version of the code that adds the spectral method with this sort of more accurate on short scales short range solver is the code. So looking at it from a sort of the integrated perspective, the code executes a number of full simulation steps. So on a real production run, this is something about 500 time steps. And then for each time step, it does some number on the order of about 5 number of subcycles where it computes this short range force. And together this comprises the whole force for one time step. The Poisson solver is this outer sort of the outer edges of this complete step, and this is uses a distributed FFT. This is written in C++ and MPI, and then everything this subcycle routines are the codes that are running sort of on the node, and these are the codes that are written in a programming model that's specific for the architecture. So this might be something like OpenMP, CUDA, HIP, SYCL. And what we're trying to model with this proxy app is what's happening on the node, right? So we're looking at the computation that's happening on the node, that's happening either on the typically like on an accelerator. And that's the vast majority of the computational effort that needs to be done to solve the problem. So, what are some of the use cases for developing this proxy app? So the way Hack has typically achieved portability in some sense of running on almost all the major supercomputers in the DOE complex is that these innermost computationally intensive kernels are written really targeting the architectures that we're trying to run on. In the production intent, we're not looking, I think, as for having a programming model that we're trying to run in a production environment on every machine, but there's a lot of advantages for us to have something like CoPA and Cabana, and see these are some of the use cases. So we'd like to have versions of the code that we can share with students, new developers. We like also some version of code that facilitates prototyping, and one that's easy for us to test new programming model backends that are available, like for CoCo's OpenMP and like HIP and SYCL and CUDA. So there's lots of advantages for us to be able to also have this kind of proxy app. So quickly, just kind of sort of how hack works, or how the short range solver works, is on each MPI rank, we have the particles overloaded with particles from neighboring MPI ranks, and these are just copies of the particles that are on a boundary large enough so that during the short range force calculation, we don't need to communicate with adjacent MPI ranks. And on the rank, the particles are then arranged using a chaining mesh. And this is just a rectangular array of cubic cells. And what's important is that the size of the cells are roughly about 3 grid cell lengths. And that's really defined by the handover force length. Why this is important is that the CM cells, when we want to compute the forces, the particle force, for any particle inside a chaining mesh cell, we only need to look at particles in that same cell or the immediately adjacent cells. And here sort of R is being defined as what that force handover length is. So that's what I'm saying is the force handover and the relationship between the size of the CM is very important. And that's why it works sort of in this way. So inside hack, sort of this is sort of at a big picture how the code works. Now what we like to do is we like to implement this same method, but now in the Cabana library. And to do that, so now I'm starting to talk about exactly what we're doing in the proxy app. So in the proxy app is basically just a standalone driver that can repeat the subcycles for one particular major time step of the simulation. So what the proxy app is capable of doing is walking forward to some arbitrary time step T1, and then computing all of the subcycles that would be done to get the particles evolved to the point of the end of the subcycling routine. So this would be executing all of the number of subcycles that need to be done for a particular time step. What to verify the code, we can just either from a real hack simulation and bring that in and do the evolution. So actually, walk up to where the simulation dumped particles, or we can generate synthetic data. So one thing we were interested in is exploring AOSOA capabilities inside Cabana. So you can imagine in the full hack code, it's not quite so simple, and something that we had been wanting to test for some time was changing the data layout. So using Cabana was a sort of a nice way for us to easily sort of test these kinds of things, or for us to experiment with different particle layouts. So we're using the AOSOA particle data structures available, and the way we map to the GPU now is using the vector length from either CUDA size or the HIP wavefront size, and mapping that to the size of the static arrays inside the structures of the AOSOAs. So this is quite nice, and something that's actually and what I was talking about earlier is sort of a use case as an easy way for us to prototype and evaluate new techniques that are not quite so easy to implement all the way in the main simulation code. And then I talked through the chaining mesh, and that's the way we organize particles so that we don't have to compare so many particles in the same node. And there's an analog to a chaining mesh available through Cabana called the link cell list. And the link cell list is really nice, and again, just a neat feature was the ability for us to build the link cell list on the GPU and kind of experiment with being able to keep particles on the GPU, or build this link cell list on the GPU. Where traditionally, in Hack, we do this on the host, and then we just sort of transfer the cell list and particles to the GPU and execute kernels that way. So it's interesting for us to be able to explore these easily explore these opportunities. And through our collaborations, we also found sort of features in the library that are not there that we like to that we can make feature requests about. And in this case, we would like particles that are not inside the boundaries of the cell list to flow into an overflow bin. So on our contribution not only to the project is of course view the library and using a real application, but also be able to make some feature requests that are probably beneficial to other codes. Sorry. So the way we're mapping the work to the GPU is by exposing concurrency at the individual particle level. So we're computing the gravitational force on each particle in parallel. And the force calculation is just the sum of all interactions with other particles. So here we're using the Cabana SIMD parallel 4. And in the red box, I'm showing the CoCo's lambda function that comes as a functor for the SIMD parallel 4. And here, the size of the natural size of the vector is it's the CUDA warp size or the HIP wavefront. Right, so that's a straightforward way that we're exposing parallelism. The proxy app is available for download in under the CoPA GitHub, and it's available for download. And we verified this with the CPU, HIP, and CUDA back. So some results. So right now we can verify the correctness of the code. We've again, I kind of alluded to sort of how we did that, but from our production simulation code, we've generated input and verification data sets simply by saving particles right before and right after we run a routine. And then in the proxy app, very intuitively, we just read the simulation particles, do the evolution of the number of subcycles, and then read the verification data set that was generated in Hack, and just particle by particle compare the relative error and positions. And so far, using the HIP and CUDA backends, using the MI250X and the V100, out of millions of particles, we see 0 particles with a relative error of 10 to the -6. So pretty convincing that indeed the codes are at least calculating the exact same answer. So performance, comparing to hack the gravity-only code that's written in CUDA, and I should emphasize that these gravity-only kernels are very heavily optimized. Our initial test showed that the Hackabana with the CUDA backend is only about 2 times slower than our fully optimized native CUDA kernels. So that was just very promising, and there are several optimizations that are still not yet implemented in the proxy app that easily account for some of this discrepancy. And some of them are things like the cell list isn't padded using the SIMD size. If you do that, you have less divergence in your warp or in your wavefront, and better coalesced memory accesses. Another thing that the production of hack uses is device shared memory, and that we've seen gives large performance boost too. So these things can be implemented in the proxy app, and they just haven't yet. The performance on Crusher is still work in progress, and I was asking questions on the previous talk, but we see relatively good performance, and it's approaching the levels that we're seeing on the NVIDIA hardware, particularly comparing the MI250X to the V100. Yeah, I think ideally we'd like to get the flops, the expected flops performance that is roughly 2.5x, but yeah, we're still not exactly there. As far as how the code scales on an individual GPU, it's almost linear. And so what this is saying is with a 256 cube, 34 cube, and a 512 cube problem size, so as you add more particles to the GPU, basically the execution time scales practically linearly. And as you would expect, because the size of the chaining mesh, which sort of is defining the number of comparisons that need to be done per particle, is fixed. So it's pretty much as you would expect. And yeah, the last I have. So yeah, any questions?
Any questions for Steve? Thank you, Steve. Okay, let's move on. And our next talk is on FFTX, on pre-exascale architectures, and the talk will be by Peter McQuarkendale.
Okay.
Take it away, Peter.
Okay, does everybody see this? There, is that full screen?
Looks good.
Okay, good. And yeah, so this is work on FFTX with my collaborators at LBNL, at Carnegie Mellon University, and SpiralGen Inc. So what is FFTX? FFTX, the project is the Exascale follow-on to FFTW, which was developed in the mid-1990s, which is an open source discrete FFT package for executing the fast Fourier transform. But now we're extending this to modern heterogeneous architectures. And FFTX also supports higher level operations. So it doesn't just do fast Fourier transforms, it does compositions of linear operators with fast Fourier transforms. And it's based on the Spiral build time code generator, which produces very high performance kernels targeted to specific uses and specific platform environments. In other words, it's customized for the different platforms. And you can learn a lot more about FFTX at our tutorial tomorrow 1 o'clock Eastern time. So this is what it looks like to to define an FFTX transform. So here we have for a specific size. So here we have nx, ny, nx equals 80, ny equals 80, and z equals 80, and then we have a domain of size 80 cubed here, and arrays, inputs, outputs, and intermediates. So these are two intermediates on all in the same domain. And the specification is the DAG, the directed acyclic graph, in blue here. So for this example, we do a multi-dimensional discrete Fourier transform, followed by scalar multiplication. So real complex diagonal times the intermediates array, and then inverse multi-dimensional discrete Fourier transform. So this is a specification for the DAG, and then FFTX calls Spiral to generate C++ or HIP or CUDA or SYCL code, typically about 1,000 lines or so, as shown here. And then when you call it from C++, you call it like this. So we have this specification which defines MDConv. And so here we have MDConv3D is one of these, and then MDConv3D.transform calls that convolution that we've defined here. So we have the input and the filter, which we've taken as another input, and getting the output. Now we've implemented this on Spock, and here we are comparing. So this is gigaflops per second. So the roofline limit is shown here for Spock in terms of gigaflop per second, and then we ran 3D FFTs. So just 3D FFTs on with Rock FFT, which is in red here, and then also FFTX after one round of performance engineering, and we can do better in most cases. There, like 3 of these examples, Rock FFT actually does better, but with our performance engineering, we're able to get FFTX to beat Rock FFT most of the time. And this is just for a 3D FFT. It's not doing the the kind of integrated algorithm convolutions with other operations. It's just a single 3D FFT. And then we've also tried this on Crusher, but so far on Crusher we've only compared Rock FFT with FFTX before any performance engineering. So again, this is a 3D FFT, different sizes, and yeah, and here's the roofline maximum we can expect on Crusher. On Crusher, Rock FFT is faster so this is about half the instances that we tried, and FFTX is faster on about half of them. So what exactly is going on inside FFTX? Well, it's complicated. So here, for example, is a specification where you do a discrete Fourier transform size 8, followed by multiplied by a diagonal, followed by an inverse discrete Fourier transform of size 8. And so specification in an operator language looks like that. And what we do here is FFTX inside it does a lifting, which is a pattern matching on the DAG. So this is to avoid a kind of combinatorial explosion where rather than searching through all possible parts of specifications of the DAG, we notice we have certain patterns, such as this one, which is multi-dimensional convolution. This one in terms of this one's size 8, and we have under the FFTX structure there are base cases, so Kronecker products and permutations and twiddle factors, and then the transformation rules for different kinds of blocking and fusing for purposes of optimization, and the breakdown rules are for algorithms. So an algorithm breaks down into sub-algorithms. So this is all because an FFT is not just a single algorithm. There are all sorts of different ways to do an FFT of a different size, of a particular size. So so we go through this whole process and we get this optimized sigma object language expression and some abstract code and finally C or CUDA HIP or sickle code, so that gets written out to a library. And performance engineering for sickle, for CUDA, for HIP, for the different platforms, it starts with particular transform, and so then we get from that, as I said, an FFT is actually a whole family of algorithms. It's not just a single algorithm because there's so many ways to break it down. So we work out a fast algorithm in SPL, the DSL for the spiral system with parallelization, vectorization, simplification, optimization, all abstraction levels. And so there's some examples here of the P's algorithm, the short vector Kuliticki for SIMT transformation. And then we do from the SPL to Sigma SPL. Sigma SPL is SPL with loops, and then optimization over that with loop flattening, regularization, and finally to the C code. So that is the final result. So this is what performance engineering is about with FFTX. And if you want to learn more, come to the tutorial tomorrow. Or if you're interested in meeting with the FFTX team before or after the tutorial, then let me know and we'll set up a meeting. I see something in the chat here. Okay, so I was asked about the FFT being real to complex, complex to complex. It's complex to complex and it's on a single node. So other questions?
Thanks, Peter. Okay, our next speaker is Mike Wall, and he's going to talk about performance for quantum molecular dynamics with Progress BML libraries.
Thanks, Sue. Is my voice clear? Can you hear me?
Yeah, I can hear you.
Yes, Mike, we can hear you well.
Okay, great, thanks. So I'm going to be talking about quantum molecular dynamics, and this involves a couple of libraries that are being developed in the CoPA project, Progress and BML. So the work I'll describe is performed by a team on the project. I've been doing work on exascale readiness. Okay. So just in terms of where we fit into the project, the CoPA project, you've heard a bit about molecular dynamics already, both long range and materials short range applications. We're looking at order n quantum molecular dynamics. We do have a proxy app that we're using. I won't talk about that in this talk. We'll be just using benchmarks that are more related to actual problems that we're interested in solving. In terms of where this connects to in other projects, like LAMPS, it connects to the Exalt project. Exalt is looking at a quantum molecular dynamics code called Latte. which is used for the materials calculations there. So what we're talking about is quantum molecular dynamics simulations at exascale. And what this means is going for long durations, but then also we're interested in looking at large systems. And both of these demand very high stability for the calculations. So otherwise we might get a large amount of energy drift over the course of the simulations, and systems might even begin exploding or behaving badly. So an example of a calculation that we previously performed is here. It's a trip cage. This is a biomolecule. And this system was 8,349 atoms total. And using the methods that we make use of, we can get very stable simulations of systems like this. And on CoPA, what we're doing is we're taking what we know about the algorithms and we are making the methods available through libraries of both low-level and high-level solvers that can be used at exascale. And those are exposed through the Progress and BML libraries. So when we talk about Progress, that's the high-level solvers. So on the right-hand side, you can see these boxes. At the top is the electronic structure code that we're using. So this could be Latte, which is the code that we use at Los Alamos very heavily, but it could also be any number of other quantum codes. And from that application point of view, the interfaces with Progress, which is this high-level solver library. And so this involves things like computing density matrix, or maybe Fermi level, something like that. And then Progress in turn is built on a low-level matrix math library called the Basic Matrix Library, or BML. And the BML is designed so that you'd have the same API for various matrix formats and types and architectures that you'd run on. So there's a C interface and there's a Fortran interface. The Fortran interface is what we use in Latte. And importantly, BML supports multiple different matrix types, so not only a dense matrix, but several sparse types. And also multiple architectures are supported, so CPU and GPU. Under the hood, it relies heavily on vendor-supported linear algebra libraries, but then also there's some custom methods, in particular on the sparse side, that we implement. In terms of building it, there's a lot of flexibility in configuring it and trying to optimize for different architectures. And it's already been ported and tested for multiple compilers and machines. So GNU, IBM, Intel, AMD, Cray, etc. And there's, especially on the LPAC side, the sparse side, a lot of OpenMP offload code has already been written. I won't be showing results on that. We're hoping that the performance of that will improve with time. Mainly I'll be focusing on the dense methods for performance in this talk. And the project is co-led by Christian Negre and Jean-Luc Fatibert on the Progress BML side. So the basic matrix library, as I said, it supports multiple formats, including several different sparse matrix formats that you can choose depending on what types of problems you're tackling. In particular, if it's a soft matter system, sometimes these sparse formats can be handy and get you faster performance. So LPAC, LBlock, and CSR-like, the way that these are structured are on the right-hand side here. I won't get into the details of those. The CSR-like, it is a CSR format, but the format's a little bit different. So in order to hook into standard CSR-based libraries, we do need to do some transformations to make that work. The GPU libraries that we use currently, Magma is what we use for dense matrix math, and that hooks into both NVIDIA and AMD hardware. We're using cuSolver in places for NVIDIA, and I'll talk about that a little bit more. We're currently implementing cuSparse. And then on the AMD side, we do have a rock solver dense matrix math implemented already, although that is less mature right now than cuSolver, the libraries themselves. And then rock-sparse also we're working on. I'll talk a little bit in an Arcticus plan slide about how we're handling Intel. And then we're using OpenMP 4.5 for OpenMP offload, and that is supported by all the vendors. Something I won't discuss here is our distributed methods, but the initial distributed methods will be released this fiscal year, and we expect that to enable us to access larger system sizes. Okay, so on the progress side, the reason why this is important for Latte is that it really implements a lot of the methods that are unique to the theory that's used within Latte. In particular, it helps us to implement the extended Lagrangian Born-Oppenheimer MD methods. And this is an approach that we've used with a lot of success to get very stable simulations out to long timescales. And the way it works is that you take your ordinary Lagrangian, which has the Hamiltonian you're interested in, and then you construct a modified one that has some auxiliary variables. Now it's an approximate Hamiltonian that you're solving at this point, but with the modifications, you can then provide exact solutions that are time reversible. And that's how we get the really good stability behavior. And over time, the solutions we come up with are very close to the Born-Oppenheimer energy surface, but there are oscillations around that surface. So that's how we achieve good stability. And another advantage of this method is that we found that we can reduce the number of SCF, the self-consistent field iterations per time step to 1. And that's down to, from something around 20 that would normally be needed. So we get a lot of the acceleration of our method just algorithmically through this choice. So Progress BML already can be used by Latte for quantum molecular dynamics. Latte is an MD package that is based on the density functional type binding theory. It's kind of a semi-empirical method. I'll describe a little bit more about that in the next slide. But it provides fast analytical and numerical physical models based on some semi-empirical tabulations, and it's fully compatible with the level 2 theory that is made available in the dftb.org parameter sets publicly available. So we can use those parameter sets. And then it provides different solvers through Progress adapted to different platforms, and also provides the extended Lagrangian method. So you can download it at this GitHub site. So the level of theory that we're using, it is a kind of semi-empirical approach that uses a reduced basis set. So compared to high-level theory with DFT, we have orbitals that provide the basis set. And so it's a very large reduction in the dimensionality of the matrices that are required, which provides a lot of the efficiency and our ability to tackle large systems. So the matrix elements come from these fits that we do of the theory against high-level theory, DFT. And we construct a self-consistent Hamiltonian using Coulombic interactions. And it works a lot like the DFTB plus code in the kind of theory it implements, if you're familiar with that. So we've already used Progress VML to improve calculations, simulations using Latte. So this gives you an idea of from runs on Summit using a GPU. So we have systems here that vary in size. These are all protein systems, some of which have surrounding water layer. The first example is about a 2,500 atom system. And what we saw is that by going from the original code without Progress VML to the Progress VML code, we got about a factor of 10 speed up. And this is important because it allows us to access longer timescales and larger systems for these methods that we're interested in studying. Similarly, for other system sizes, if we increase the system size, we get at least a 10-fold speed up. In the largest system we test here, 6,000 atoms, we actually saw a speed up of a factor of 15. So, this is work that we've done on the ECP project. Getting to performance on Crusher. So I'm going to focus here on some benchmarks that we developed that test a density matrix solve using different methods. So the method that's kind of featured here is this SP2 method. This is an iterative approach for getting the density matrix, and it's based on performing a number of matrix multiplies until you converge on a solution. So I'll talk about that one first. Here you can see in blue, this is performance on SPOC for various matrix sizes. It's a log-log plot. You can see there's a quadratic scaling line on here in orange and a green line that indicates cubic scaling. So this method uses, I think, Strassen under the hood, which should be close to cubic scaling. And so we get scaling that seems to agree with that at large matrix sizes. If you look at Crusher versus SPOC, Crusher is in green, SPOC is in blue, and the Crusher times are faster than SPOC, so that's as expected. And then for reference here, there's an A100 NVIDIA performance using a machine here at Los Alamos. And we're seeing that at the larger matrix sizes that these dense SP2 methods are performing a little bit better on Crusher than on A100 Magma. All of these methods, so it should be taken in context. So all these methods in this case are using Magma under the hood to perform the matrix multiplies and other matrix math. So moving over to diagonalization. This is an important method for us as well. Sometimes this is actually faster depending on the system that we're looking at. So we do make use of this. And you can see on SPOC in blue, comparing SPOC to Crusher, Crusher is faster than SPOC. And at large matrix sizes, we can see that the behavior is approaching something between the quadratic and the cubic scaling. So we think at large matrix sizes, this should go cubic. And what we see, though, is that using the A100 and a different method, the Q-solver method that's available for the DSY-EV eigenvalue problem, the performance is quite a bit faster using that method compared to the Magma method. So currently, this at the largest matrix sizes, this dense diagonalization at the 20,000 sizes is our fastest method. But this should be taken in context. So first of all, this is work in progress. The methods we're using are Magma for the AMD hardware. And then we're choosing Q-solver here because that's our fastest method, okay? It was already very highly optimized for NVIDIA. The Magma tests, we're not yet making use of the 2.6.2 release of Magma. Corresponding with the developers, it sounds like possibly there could be up to a factor of 2 improvement compared to what we're seeing here for the 20,000 matrix size. So we're looking forward to testing that. Also, Magma has a 2-stage reduction that they've implemented. It's not yet quite as performant as they'd like, but when that performance is addressed, that might actually be a faster method than the one that we're using. And then also we attempted to use Rock Solver, which is AMD's version of the cuSolver library. But for this particular method, DSY EV Rock Solver performance was very poor so far. AMD is aware of that issue, and the latest is that a revision is expected in that method by ROCm 5.3. So all these are still work in progress, and we're hoping to see better times in the future. Briefly on Arcticus, I don't have performance results on this that I can present, but our plan here for the dense methods is to use OpenMP offload to allocate data on the GPU and move data around as needed. And then to use vendor optimized kernels for the compute. So the way this is done with 1MKL is we can use target data regions to allocate the data on GPU. And then whenever we want to call a 1MKL method that makes use of the GPU, we can do that within an OpenMP offload target region. And so this approach works in cases that we've looked at. And so this is our general approach that we're working on right now. And our sparse workflow is still under development for this architecture. So again, I'd like to acknowledge the Progress BML team and also the CoPA project team, funding from the DOE Exascale Computing Project. And really, all of this progress relied very heavily on the consultants, both at Oak Ridge and at Argonne. They've been very responsive and helped us to address a number of issues. And when there were compiler bugs that needed fixing, they helped us to get those bugs reported to the vendors and get those fixed. So kudos to them. Thank you.
Questions for Mike? Thanks, Mike. We'll move on to our next speaker, Sam Reeve, who's going to talk about performance of Cabana, the Cabana library on early exascale architectures.
All right, hey Sue, can you see my screen?
You need to go to presenter mode. Are you in?
Oh, let me swap. How's
There
that?
you go. Good. Very good. Go ahead.
All right, so yeah, I'm Sam Reeve, and I'm currently leading the Cabana library development as a part of CoPA. I'll talk both about Cabana as well as the partner application Picasso NPM developed as part of Exascale. So I've listed the Cabana development team here. Certainly this is a big group effort, and I've folded Quite Chong and Austin Eisner specifically because they ran, I think, almost all the results on this talk and helped me out quite a bit, but certainly the whole team is very important to moving this forward. So I think we've seen different versions of this slide and most of the talks, just highlighting that of the 4 application partners, Cabana is directly supporting both the new Picasso NPM application as a part of Exascale, as well as been added to XGC, and also is interacting with both the hack and LAMP codes through primarily proxy applications, but also ideas back and forth in terms of those production code development. So I'm sure if you've ever seen me give a talk, you've seen exactly this slide. Cabana itself is intended for to support any particle application with both a particle as well as structured particle grid interactions. And it's built on Cocos for the on-node performance portability, and then adding MPI on top of that, as well as a growing number of optional libraries that support specific features. So with ArborX, we have an optional neighbor list interface to use their tree structures, and similarly with Hepty and Hyper for specific additions to the library. So again, I'll focus on Picasso NPM as one feature, and you've already heard about a number of the other interactions here. So across Cabana, we focused on building benchmark kernels that let us focus on specific parts of the library, since it's mainly built as a toolkit to support different applications. I've bolded the ones that I'll talk about today. Certainly Steve talked a lot about the linked cell list as the foundation for the hack Cabana proxy app. And quite a few of these heavily influence the performance of the Picasso NPM application, but certainly not all of them. So I'm going to start just by jumping straight in here. All the benchmarks are set up to scale across different particle counts as well as specific variables of interest. So in this case, we're looking at performance, not a particularly fair comparison, but a single CPU and a single GCD on Crusher, so a single MI250X to a single EPIC core, which again is just based on the fact that these benchmarks, or most of these benchmarks, are built to run on a single rank, and then to except for those communication benchmarks. So here in red, I'm showing the time to create the neighbor list. So searching at a fixed neighbor cutoff radius, which is the feature that we see in the separated lines, right? Each one is a single cutoff radius. So the more work we put in, the more time that benchmark takes. And then the blue lines here are the neighbor iteration time. So this would be akin to the force interaction kernel in a molecular dynamics app. In this case, a very, very simple kernel that's not anywhere near representative of something as complex as Snap, like Stan was talking about earlier. The more interesting comparison here is a single GCD on Crusher compared to a single V100. In this case, we see a split where the neighbor list creation time is somewhere between parity and maybe 1.5 times speed up. So that's a good thing to see, but the iteration time, even in this very, very simple kernel where we're just summing the neighbors across the within that neighbor radius, we see reasonably significant slowdown here, and a lot of this is going to be related to the very detailed comparisons that Stan showed earlier, and certainly something that we need to focus on within the library. And like I showed on the previous a couple slides ago, we've got a few different versions of neighbor list benchmark across the different types of neighbor lists. So that's something we're going to continue working on. This specific implementation is, I think, representative across the different options. So moving from here to the next benchmark, which is the particle sorting. In this case, we see a somewhat similar trend, but more pronounced, where the small system sizes are faster on the V100, and the largest system size is faster on the MI250X, where again, this is intended to be a benchmark for a single rank. And the two different lines you see for the actual sorting, the permute in blue here, is whether or not we're sorting a single particle property or sorting all the particle properties together. And the creation line here is just building the permutation vector without actually doing the sort. And just as a note, in Cabana, we can not only sort the particles, we can also bin them with a binning size greater than 1. And in that case, it really just echoes the previous slide, where a little bit more noise to it, since each point is not only the way the number of particle properties we're sorting, but also the size of the bins that we're using in this case. So we see the same trend across system size, and the degree to which we can optimize the small systems, I think, is something we have yet to be seen. So moving on from here, I'm gonna show some slides that where the plots are not maybe particularly interesting at the moment, but some some important things to focus on. So this is the particle migration. So the schematic I've got on the top right here is showing, we're moving each particle from a unique decomposition based on some spatial MPI domains and moving it from one unique rank to another. And the spread of the data in this case, we're doing multiple runs based on the fraction of the total number of particles communicated. And I apologize, the x-axis is incorrect here. This is number of particles, not grids. And it's in fact the number of particles per rank. So it's a relatively fair comparison looking at here at a single node across the machines, but a fixed number of particles per rank. So the speed up numbers look good in this case, which is nice, but really what this is telling us that it's not the best or not the end all be all in terms of comparisons, where we've had some very good interactions with our contact at NVIDIA and Weinberg, and we're moving closer to add in a new variant of our communication routines, which avoid a lot of relatively expensive buffer allocations, which is hurting us quite a bit on Summit, where so once we've updated that, we would expect it to improve performance on both Crusher and Summit. And until we do that, we can't really fairly compare these things. And so we'll have to move toward it at the same time, move towards more objective performance comparisons. A lot of the details that we've heard from the previous talks. So the next slide here is showing the particle halo performance. So ghosting particles from neighboring ranks based on the distance to the particles on the current rank, and both building the steering vector in terms of where those particles need to be copied to as well in red, as well as actually doing the update across ranks here in blue. In this case, showing the gather operation, but we have very similar results for the scatter operations. Again, showing the spread of the data in terms of the fraction of particles communicated, and a pretty similar story where the buffer allocation is hurting us quite a bit more in Summit, and so there's not a lot to be seen here. In the interest of time, I'll jump to the structured grid subpackage in Kibana, which is called Kahita. And so looking at the grid halo here, the overall speed of numbers are pretty similar, since it's fundamentally still winning on the buffer allocations here. But the data is at least a lot more structured because it is a structured communication. So in the schematic on the top right here, we can modify the size of the halo width here, which is just a fixed number of grid cells. We're modifying this from 1 to 5 grid cells in this case. And some interesting things to note here is that at the very bottom, the bottom pair of points for both creating the steering vector for the communication as well as executing that communication is a halo width of 1. So both in speed up as well as in the total time for each GPU to do that communication is by far cheapest on the with a halo width of 1. And then there's a smaller spread as we move up here, so that the application level, if we can get away with using a halo width of 1, that might end up being best. Or if we can use a halo width of, if we need to use a halo width of 2, we might as well, in a lot of cases, use something that's even larger and try to reduce the frequency of communication instead. So switching back for the final Kibana benchmark comparison that I'll show here, this is the particle grid interpolation. So the red and blue points in this case are showing the particle to grid interpolation, as well as blue the grid to particle, showing the schematic in the top right again. In this case, we're back to a single rank comparison because the communication here is a relatively small part of what we're trying to test in terms of performance. And here the spread of the data in the plots is going to be both the order of the field we're interpolating, so scalar, vector, tensor, as well as the type of interpolation we're doing, so either interpolating the value or the gradient, etc. So in this case, we see with 1 particle per cell and scaling the total number of grid points, we get, in a lot of cases, a noticeable slowdown. That certainly has an overall trend to improve as the system size is increased. And I'll note that the particles per cell, in this case, is 1 as we jump to 2 per spatial dimension, so 8 total particles per cell. We start to see some improvements in terms of the speed up numbers, where the overall the grid to particle operation ends up faster on Crusher, where if we jump even farther to 4 particles per spatial dimension in a uniform setup here, we see that in almost all the cases here, we get a speed up again within that, up to maybe a 1.5 overall speed up, not quite the 2.5x speed up of the peak flop difference, but certainly something that's encouraging. And moving forward, this is a very important kernel with respect to our NPM app. So that's a useful transition to go very, very briefly into how the Picasso NPM application fits into the XAM Center overall. So XAM has a pretty large workflow and a large number of different codes working as a part of it. And so the main problem, the main threshold challenge problem doesn't include Picasso NPM, but NPM is intended as a high fidelity version of the workflow where we replace the finite volume thermal transport code with our NPM application, which is going to be able to do both the heat transport, but also fluid flow and surface deformation, to then pass on to the microstructure prediction and the final property prediction codes. So jumping ahead to the performance here, this is just a single individual test problem. So it's a stationary spot melt in this laser powder bed application where we're fixing, in this case, fixing the position of the laser, where in the real application, we'll be moving that laser around as we build up this total additively manufactured part. In this spot melt problem, I'm showing the snapshot on the left where we're looking at the heat field coming due to the laser on the left-hand side, and then the phase transformation on the right-hand side where we're melting very localized here. And we're showing the performance of this. I should have noted this is the fraction of time per kernel on a single Crusher GCD, and breaking it down to the main kernels that are hopefully somewhat familiar from the previous benchmark that I showed. The particle to grid interpolation is noticeably the most expensive. The temperature update based on the divergence of temperature in blue here is also heavily dominated by the additional particle to grid interpolation update. And then in green, the grid to particle update at the end of the step is also relatively expensive, and the rest of the grid updates in between, the other 3 colored bars here, are relatively inexpensive. So the non-CoCo's time in this case is very cheap, or I should say the non-CoCo's time is almost entirely MPI updates, which is very cheap because this is on a single rank. And so this outlook of our total application for this test problem time to solution hopefully makes it easier to understand the next few relative comparisons. So again, going back to the speed up comparisons of both CPUs and GPUs in this case, a more fair comparison looking at the full CPU node here compared to a single GCD or GPU. We see a pretty good speed up, about 5x for the full CPU node on Crusher, and then about parity between a single GCD at this system size, where we notice a slowdown in the P2G kernels, which is going to be related both to the particles per cell we have from that benchmark kernel that we see here, and the total system size that we're looking at. So we can try to use that benchmark to drive improvement in this specific comparison. And the rest of the kernels are pretty near parity for this particular comparison. So jumping to the next slide, start comparing only the Crusher and Summit GPUs. In this case, there are 2 important differences, both that we're jumping to comparing a node to node. So it's tilting the favor already towards Crusher, but also in bumping up the total particle count slightly, we're starting to also get a real speed up in favor of Crusher. So starting to see overall improvement, particularly in the heaviest kernels, the P2G and the divergence of the temperature update. And again, near parity in the rest. Now that we're looking at a full node here, we have some some relative, some reasonable amount of time in MPI, so that's overall a win that connects back to the other benchmarks we looked at on the Kibana side. But at the same time, we do have one important thing to improve within Kibana, which is not doing the MPI communication itself or allocating those buffers, but in filling those buffers, we do see a noticeable slowdown, which is something we're going to need to investigate on the Kibana side. One more example here, just showing that if we bump that particle count up pretty significantly and put 140 million particles in total on the node, the relative speed up per kernel is pretty similar. So one last detail, certainly the intent of the NPM map is to add even more physics and act as a high fidelity component within the XAM workflow. And so this is showing our new and developing capability that basically doubles the number of kernels that we're looking at here. And in this case, we have not only the thermal update, but also the mechanics-based update, which really looks very similar. And we see, again, similar speedups across these individual kernels. But we also end up having kernels that are focused on the free surface motion, which is the purple and pink one here, where we're making calls down to ArborX to generate some surface particles here. And so each of those are additional things for us to focus on as we move forward. Again, this is a very small system size and a very new result here, so totally bear that in mind. To go ahead and conclude, we're focusing on benchmarks across the Kibana library, sweeping across particle grid sizes and various parameters of interest. Performance comparisons are starting to look pretty good across Summit and Crusher, with some very clear places to focus based on connections to different applications. And I think it was Stan earlier that mentioned, one of the flags, the OLCF Crusher hackathon, was very helpful for us to get these performance numbers moving in the right direction, certainly. And continuing what we need to move forward into more detailed profiling, things like roofline analysis, and also continue adding even more benchmarks to help moving towards improving all the partner applications. So with that, I'm happy to take any questions.
Any questions for Sam? Okay, thanks, Sam. And we'll move on to our last speaker, Aaron Scheinberg, who's going to talk about XGC and Kibana and Cocos on Crusher. Take it away.
Hi, okay, can you see the screen?
Yes.
Looks okay. Great. I'm Aaron Scheinberg. I work with XGC and preparing it for Exascale. And I have a big team with the XGC group. A lot of these figures were done by Kevin Huck, who has done a lot of the Crusher work. The XGC is a fusion plasma physics code. It's also in another ECP project, ECP WDM, the whole model device. XGC specializes in edge physics with realistic geometry. And so in this proposed coupling with XGC and Gene or GEM, which do core physics more efficiently, the idea is that XGC will handle the edge. The vast majority in this coupling of time is spent in XGC, so optimization is critical for us. General challenges that are coming with this optimization is that XGC supports a wide array of physics features, and they all have to be supported as we prepare for Exascale. There's different modes of operation that drastically change which routines are the bottlenecks. And also physics is in a constant state of development with not only additional new modular features that need to be added and offloaded, but also fundamental structural modifications like as I'm refactoring the code, I have to keep in mind that there's going to be a future stellarator code that ideally would be one code base or implicit time stepping. And how do we write code in a way that will support all of this in the future as well? XGC is a gyrokinetic code, so it's reduced from 6 dimensions to 5 dimensions. It's a particle and cell code on an unstructured 2D grid. So this is a cross-section of that tokamak that you saw in the previous slide. And there's an unstructured grid on this poloidal cross-section, whereas the toroidal dimension is structured. So then the domain decomposition is each MPI rank handles a different subset of these planes radially. So that's what these colors represent. Each one is a different MPI rank. And the general algorithm of XGC is you have particles that are scattering onto this unstructured grid. Their charge and current, which is used to solve for the electromagnetic field of the next time step. The electrons and the ions get pushed to their new location. Because the electrons move a lot more quickly, they can be subcycled about 60 times in the electrostatic case and around 6 to 10 times in the electromagnetic case. After the particles are at their new position, then they have to be transferred between their MPI ranks to their new homes, and then a number of other physics occurs as well as diagnostics. So our approach to transitioning to getting set up on Exascale, it also involved transitioning to C++. Prior to this, XGC had some kernels that were running on GPU with OpenACC and CUDA Fortran. And our initial decision to adopt Cocos and Cabana came with this idea that we would stay in Fortran and use wrappers and macros. So we would have something like the code in Fortran, and then this interface in C++, and then the kernels in Fortran as well. And that was actually a feasible strategy for just Summit when we just are able to use CUDA Fortran inside for these kernels, but it's less clear what we would have done with AMD or Intel GPUs. The interface is also limited a lot of functionality that is otherwise useful. So, so otherwise, we might have been using OpenMP Target if we had chosen to stay in Fortran. But by transitioning to C++, we have better usage of Cocos Cabana features. And then, there are other advantages that come with just being a C++, I believe, earlier compile support. But, the downside is it's a lot of work to convert the code. On the other hand, if we're refactoring to offload everything, we might as well convert it to C++. So that sort of conversion basically involved looking for a self-contained part of the code, some kernel that you could reasonably identify as modular, identify inputs and outputs, and then create interfaces to get the inputs and outputs. And that's sort of some snippets of what that code looks like. And so you can imagine over time, we have more and more of these interfaces with the C++ and the Fortran code until eventually most of the code is in C++ and you start removing these interfaces. And so I'd say we're about here in this process. So another question was why not just write everything from scratch instead of just instead of doing what we're doing and writing all these temporary scaffolding type interfaces. So we're essentially replacing every part of an airplane while in flight. And the idea here was that, even though there's time spent on those interfaces and time spent dealing with legacy structures and features, we get to keep a single code base, and the code is kept up to date as new physics capabilities are integrated. So there's no divergence. And the code also gets continually tested in production conditions. Whereas if we had gone and just had a separate code for Exascale and C++, then we wouldn't have had to deal with those extra interfaces, but we also wouldn't have gotten the benefits of the code in production on Summit as we've been making these improvements. So for reference, on Summit, this is timing for an electrostatic simulation. The the offloaded version runs about 31 times faster than the CPU only version right now, and about 1.85 times faster than the pre-CoPA code base in 2019. So here, these are different points in time, and these two columns are CPU on the left and GPU kernels on the right. And so originally, as I said, we had CUDA, Fortran, and OpenACC in our major kernels. But as we've transitioned to Cocos and Cabana, and then taken all of our kernels and gradually, as they become more bottlenecks, move them onto GPU, and then now we have much less idle GPU time and a faster code. Just a quick mention for Perlmutter, because this is just a pretty impressive timing that we get there. Now, from now on, we're going to be looking at electromagnetic simulations because they're the priority physics-wise going forward. And a difference here is that the electron push is less important because it's subcycled fewer times. So we no longer have this one big kernel that's really important. But on Perlmutter, we get about 2.1 times faster than Summit with the same number of GPUs. So this is a weak scaling plot, and with time step on the left, and you can see Perlmutter's going a lot faster. But Crusher, I'll get to another weak scaling similar plot, but first just wanted to look at individual kernels, because most major XGC components now have standalone kernels for easier testing. And these kernels are demonstrating 1.2 to 1.6x speed up when comparing one V100 versus one GCD or half a MI250X. So the theoretical peak flop rate ratio for double precision is like 3, but these numbers seem to be in line with what most other codes are experiencing. So this is a similar comparison plot, electromagnetic full simulation. And this is a weak scaling plot that shows about 1.3x speed up if you're comparing, again, one V100 versus one GCD. So the weak scaling is decent. There's a lot of kernels that need to be optimized that were not optimized yet, partially because they were not as important in the electrostatic simulations, which is the big focus before. So there are a number of kernels that still remain on the CPU. So even just offloading is still more of a priority to deal with bottlenecks than fine tuning in a lot of these kernels. So you might ask why GCD versus V100, and it seems that there has been a lot of discussion about what is the relevant comparison to make, and I'd say that depends on what you care about. So to deal with that question, I realized you can just do a strong scaling. So this figure shows the number of GCDs on your x-axis and then a speed up compared to a reference run on Summit. So all 5 of these points are the exact same problem size. And so this point is run on Summit with 256 V100s. This point is run with 256 GCDs. And so this black line is saying, is this the perfect strong scaling, where you'd say, okay, I have twice as many GCDs, so I expect twice as much performance. And so if you care about how an MI250X compares versus a V100, then you care about this point. If you care about GCD versus V100, you care about this one. If you care about equal flops, then you care about this intersection. And I think a really relevant point for actual production runs is this equal device memory, because basically what we're going to try to do on Frontier is we're going to say, okay, we have this problem that fills up Summit, and then let's say that we want to run that problem on Frontier. How many GCDs do we need? And just scaling naively for memory, amount of device memory available, we can fit a problem size that's about 4 times on a on 4 times fewer resources. So that's why I think that this is kind of the relevant point. And if you look at the ratio of Summit and Frontier device memory that will be available, and I'm not sure if this is an estimate on my part, but the more science-oriented maybe way to make the comparison of the machines is to say that on Frontier, we're going to run a physics problem that's going to be 8 to 9 times larger than what we could do filling up Summit. And those time steps are going to take about 2.x times more time. So I think that's kind of the best way of comparison, but there's a lot of options. And that's of course just the current performance figures. So we're expecting to improve those a lot. So wanted to look at some specific kernels. The electron push kernel is still a large kernel, although it's not as dominant as before. On Spock, we were having issues with atomics, but these have thankfully been resolved on Crusher. So when we look at this figure, that's particles per GPU on the x-axis and time per particle on the y-axis. This is the Spock line in blue, and then the V100 in red, and the MI250X, this is 1 GCD, is now outperforming it. We've had an issue with high register pressure, and one experiment there was we broke up the kernel, so kernel fission there, which got us a 27% speed up on Summit and a 12% speed up on Crusher. Adjusting the launch bounds also accelerated the kernel on Crusher by something like 25%. So that's this figure here, experimenting with different launch bounds. Unfortunately, they weren't really additive to this 12% speed up. Because I think they're fundamentally solving the same problem. Another issue is a high number of integer operations. I think the index calculations are blocking the optimal FPU usage. And we're also aware that the L1 cache for the MI250X is smaller than V100, and that this might be an issue. But we're still waiting to do more profiling to figure that out. Another large kernel is our collisions kernel, which consists of thousands of small, embarrassingly parallel problems where each mesh vertex on our unstructured grid is doing a very small problem. And this was originally difficult to do, to fill up a GPU to do anything in this kernel, but we now do batching. So we take a whole large number of these vertices together and solve them in parallel. And that helped with the matrix construction phase of the collisions, but then there's also the solver, which is still using LAPACK on CPU. And so there's this rather large GPU idle time. And to solve this, we have the Ginkgo's GPU batch solver, which is being integrated into XGC by Dhruva Kulkarni. And the solver itself seems to be 2.5x faster. And that's going to speed up our collision kernel by about 1.4x. That's these points as a function of batch size. We've also been looking at the particle shift on Crusher because we now have GPU-aware MPI as an option for XGC's shift kernel. This has been tested on Crusher, and we get a large amount of savings from removing extra CPU allocation time and extra CPU-GPU communication. So that's most of this drop here, going from the regular MPI to GPU-aware MPI as a function of Crusher number of nodes. But actually, the MPI communication itself, it seems that the GPU-aware MPI gets slower as you get to large number of nodes compared with the MPI CPU to CPU. So we're trying to figure that out. One last thing that I want to talk about was particle memory management. Whether we want our particles to reside on the CPU or the GPU, and whether that might be different for different architectures. So the current default that we use is we have all of our particles on CPU resident there, and then they're sent to the GPU to do whatever operation, and then sent back to the CPU. The next species goes up. Alternatively, if we have enough memory on the GPU, then we can just leave these particles here. Or we've also been looking into asynchronous streaming, where we're able to transfer the particles up to the GPU and effectively hide that communication time by doing it as the kernel is executing. So that has led to development of what I've called a streaming parallel 4, where it's basically the same as a CoCo's parallel 4, but you also tell it which views or AOSOAs you want to transfer back and forth to the host and the device. And what's happening is that this host data, which for us is particles, is split into chunks. And there are 3 streams where one GPU stream is sending this to the GPU, while one is executing the data that's already there, and one is returning the data that's already completed the operation. And on Summit, this has been really effective in testing to be able to hide pretty much all the communication time. The only issue is that it has to be copied to pin memory, to pinned host memory first, which introduces an extra step. But that also is pretty effectively hidden. On Crusher, I've had some progress with this, but it appears that it's not fully asynchronous, so I need to resolve that. There's also promising testing on Sickle, which suggests this is going to be pretty portable, and it's not integrated into XGC yet, but I'm hoping to do that, or to add it as part of the Kibana library so that others can use it as well, and then we can use it from there. So to summarize, we've had steady progress in porting kernels to the GPU via Cocos and Kibana. There's no major hurdles foreseen for exascale science production on Frontier. And in the future, we need to do more detailed profiling on Crusher to understand if we can speed up those numbers more. And then there's still a lot of opportunities for optimization, especially with the new electromagnetic code, including communication routines, load balancing, and computation. Thanks. I think I've run over a little bit, but there's time for questions.
Aaron, there's a couple questions in the chat.
Oh no. Oh, wow, there's 10. Wait.
Zemming Jin, do you want to ask your questions?
Yeah, I'm sorry. I didn't see the...
Thank you. I was wondering if some tool translator can translate Fortran to.
Yeah, that's a good question. Yeah, so I have looked around, and ultimately I ended up writing my own tool that yeah, I don't think you ever want to use something that's just fully automated. So I'm experimenting with tooling that's not fully automated, but that will still at least take care of the really busy work of adding semicolons and that kind of thing. But yeah, I think ultimately you need to understand what the code is doing. And I don't think there's really automated systems that understand well enough to make sure that your code is structured the way that you want it.
Oh, I see. Also, for the electron push kernel, is it FP60 atomics?
Yes.
Oh.
Yeah. So that was the issue on Spock. That wasn't well supported, but yeah, on Crusher, that's working well.
Oh, okay. Oh, thanks.
There was another question for Sam in the chat from Scott. I think he answered it, but maybe you guys want to talk about it.
Yeah, I mean, certainly for the Cabana library, I'd be very interested in working with Exa.io. We should yeah, exchange email maybe.
Yeah, sounds good. So do you have performance numbers? So does Silo work on the newer machines? Probably.
Yeah, I mean, it's certainly working to get us output that we can use, and a lot of what we're doing in that project is developing new physics capabilities. So we're not really pushing huge systems or scaling yet, but we could certainly get those performance numbers and start the discussion that way.
All right, thanks.
Appreciate it.
Okay, that was all of our speakers. You heard a lot about CoPA and all the interesting work that's going on in all our performance on Crusher capabilities. Are there any other questions for any of our speakers? Or any discussion you guys want to have about anything? We did see a lot of cases where we're seeing good performance or better performance on Crusher than on Summit, and in some cases where we're not, and some where it's very specialized, and we're still figuring those things out. So any other comments or questions before we close?
I was just wondering why people compare MI250 with V100, not with A100.
Well, I can at least answer for myself, where it's just easier to use the two OLCF systems here at Oak Ridge, but that's just my own personal bias.
Yeah, that's the same for me too.
Is there A100 at OLCF? I don't think so. Is that right?
Yeah, certainly not in a large system that I'm aware of. But certainly something that we should at least at the Cabana level do some more work with.
Oh, okay.
And I know Stan, you had some good numbers there, and Aaron as well, I believe.
Isn't Perlmutter, doesn't it have A100s on it?
Yes.
So that would be a larger system to test the A100s on.
Yes.
But Perlmutter has a previous generation interconnect.
Okay.
It does not have the Slingshot 11. It has Slingshot 10.
Okay. Any other comments? Okay, thank you so much for listening to our session, and have a good afternoon.
Thanks, Sue.
Thanks, Sue.
Thanks.